Okay, guys, this is section 3.1, part 2. So let's take a look. So we're still talking about lines. We're still talking about linear function. All right, so this says the following table is taken from the 2013 federal income tax table provided by the Internal Revenue Service. It applies to a married couple filing jointly. Okay, so here's our chart. It says, what is the growth rate? Okay, well, let's think about what does growth rate mean? Growth rate means slope. So growth rate is slope. Slope is change in y over change in x. So we can just do it from a visual standpoint. What is this changing from? How much is it changing each time? If you spend a little time, 41,000, 41,100, 41,200, 41,300. So that is going up by 100. Okay, so this is each going up by 100. Remember, we should really check. It should always be consistent. We really should check that. This might be just a little bit harder to see. You can kind of compare the two, take a little bit of time. But if you check, it would be going up by 15 each time. Now remember, if you don't know for sure, if it wasn't as obvious as the 100, just do y2 minus y1 over x2 minus x1. Okay. So just make sure, and even if you saw this, make sure that you put the y over the x. So even though I sometimes do x first, make sure at the end of the day that you put y over x. But if you just wanted to check, let me just slide this over. And you could pick any, you could do the first two, or maybe do the first two to see the difference and then double check to make sure that it is always the 15, because we really should see that it's consistently first 15 before we say that it's linear. But sometimes it's a good idea just to do the first one. So, and make sure you do y2, so 5,002, oh, this is for x, right? I think y, I think for, oh, we were okay, yeah. What am I saying? So let's do 5,276 minus 5,261 over, and then this one I was going to say, I think we could clearly see it, but if we just want to write it, that's okay. 41,100 minus 41,000. Okay. And then if you officially subtract these two, then you do get 15. And then what you could check is just to make sure it's always plus 15 for the rest of them, because they really should be the same throughout before you identify that it's completely linear. Okay, so this is what, 15 over 100. We could reduce that down. We could also just write it as 0.15 instead of a fraction. If we just write it as a decimal, that's perfect. Okay, the fact that the growth rate over each interval is constant, right? Because it's the same throughout, and that's why we said you probably should check each interval, tells us that the tax owed is a linear function. A linear function of income. Okay, so now they just want us, can we, basically this sounds pretty official, let T be the tax owed in dollars and let I be the taxable income in excess of 41,000. Write the linear formula for tax dollars owed in terms of income. So tax dollars in terms of income. So tax dollars in terms of income. Okay, we know it's linear, so this is y equals mx plus b. But instead of y, they want us to do tax dollars in terms of income. So that's I. So we need slope, we need the growth rate. That's this guy, 0.15. So T equals, remember, slope and growth rate go together. Okay, so that's 0.15 I. And then this one might be a little bit harder, but remember, B is always your starting point. B is always your starting point. Oh, we could also go up here maybe and say this is X and this is Y, but here they wanted us to do I and T. They just gave us different letters. So remember, this goes with this guy too. So what is the t value at the start of the problem? That's the 5,261. Okay, and that's it. That's the equation. Here it was saying they also, what they did here is they graphed these points. These points are graphed here, and they just said visually you could also see if you graph it that it does in fact form a line. So that's all that they were doing there. They said the data was graphed and notice the linear function passes through each of the data points, which verifies the validity of our linear formula. Okay. All right, so let's see, what's page 2. Okay, so here's what they were getting at. Let me bring this back one more time. They said these form a perfect line, and up until now, we've always seen, you know, if we're talking about a line, yeah, it forms a perfect line, right? That makes the most sense. But our book uses this little phrase. Let's try like this. Okay. But is close enough okay? So what they're saying is, what happens if things aren't perfect, but there is some correlation that kind of looks like a line? What that is called, if your data doesn't fit a line perfectly, but you can kind of relate it to a line, that's called a linear regression, a trend line, or a line of best fit. Those are all the same thing. It's just whatever people like to call it. Let me know, this isn't on your note sheet, but I think this might be a good example. I think it's even better than this one, so we'll get to that one in a minute. But this next sheet, and then we'll come back to this. There's 4 graphs here. This is just data collected. Does this one form a perfect line? No. But we don't want to toss it out. We want to say, could we draw a line in that's pretty close to the data? Is the data close enough to a line that we can draw in a line that kind of represents the data? It's not perfect, but it represents the data. And I think this one is a good example. We could draw a line in here. And do we see how a lot of the points are pretty close to that? And this then would be called a line of best fit or a linear regression. It's not perfect, but the data fits a line close enough. Okay, let's take a look at B. Does B fit a line? I don't think B fits a line. We could maybe argue maybe 2 lines or something, but if I want to do all this data together, if I draw in a line like this, then I'm saying this data should be up here. So I don't think I can draw in one line and have it fit. So sometimes the data forms a general line, but sometimes it's just not possible. And you can also do like exponential regressions. You can also do parabola regressions. They're called parabolic. So if it doesn't fit a line, that's okay. There might be some other option. Okay, let's take a look at C real quick. Do the data points form a perfect line? No. But could we draw in a line that could at least come pretty close to representing the data? And that would be this guy, right? And I could maybe, if I spent a little bit more time, maybe I could have even kind of come up here a little bit more. But I think in general, we could say that this data tends to fit a line, even though it's not perfect. Okay, now let's take a look at D. What do we think about D? Does D fit a line? I just don't think so, right? This one's even kind of all over the place. This B, we maybe could do something with a parabola. Maybe. This is a little iffy, but this is all over the place. And that's okay, too. This just doesn't represent a linear function, and that's okay. This one is not a perfect linear function, but the tendency is there to draw in a line, and we can use this line in general to represent the data. Because realistically, very rarely are you going to collect data that forms a perfect line. But a lot of times it's pretty close, and you can use that line instead. Okay, so let's take a look. What is this saying? Okay, so we're talking about this linear regression, or I kind of like this phrase, line of best fit, because it kind of reminds you that, okay, it's not covering all the data perfectly, but it is pretty close. Okay, so the example above fit a linear function perfectly. Oh, let's go over that. That was this guy here. Okay, this fit a line perfectly. Okay, so the example above fit a linear function perfectly, but a lot of data sets are not perfectly linear. Okay, but could be approximated by a linear function. So could be approximated. Could be approximated by a linear function. Okay, line graphs. Line graphs are used for more individual data use. So if we want to just remember what a line graph is literally connecting the points. Okay, and then a line of best fit is just one solid line that all of them kind of relate to. So a line graph, if I want to specifically calculate the slope, then I'm going to do a line graph and actually calculate the slope of that line. But if I just want a general fit for all the data, then I'm just going to draw on that line and use that line as my data information. Okay, where trend lines or line of best fit, our book likes to use this word trend lines, where trend lines are used to tie all the data together. There's one line, we use this slope of this line for all the data, even though we can clearly see that if we calculated each of these slopes, they would be different. Okay. They show data trends as a whole. We're kind of combining them all together and just using one line instead of like what we learned in chapter 2, a line graph, and we found each slope individually. Okay. Now this line, you can calculate these. This is going to be one project that we were going to do. You can actually calculate these lines of best fit on Excel. But here I just did it here on my own, but you can actually plug in your data and then have it calculate a line of best fit. Trend lines should show the general trend. It's a real original sentence, right? I just got that from the book, but trend lines should show the general trend, hence the name, right? That only makes sense. They do not need to go through any points. They don't actually have to go through any points. They just have to be kind of like in the range of the points. Within reason, the data points should be close to the trend line. Okay. So they don't necessarily have to go through any. Sometimes they do go through at least a couple, but technically they don't have to go through any. It just has to kind of form in general the line. The data has to form a general line. Okay. All right, let's do some examples. This one's pretty close. But I think if you looked close enough that, you know, this goes here. If we were doing a line graph, maybe these are pretty close, but this would definitely angle over a little bit. But if you can kind of see, and I'll draw it, let me just turn it and then I'll draw it, turn it back. They drew in a line of best fit. Okay. And you can even with that, you can kind of see that this dot is above, these dots are below, even though they're pretty close. This one is definitely a little bit more above, that's a little bit below. But in general, they definitely fit a line of best fit. Okay. All right, so what is the slope of the trend line? Well, we could do some stuff by calculating it by hand, but a lot of times it's nicer to have a computer or something calculate it for us. And that's what this is. They actually had it calculated for us. So the slope is literally that 2.0298. That's it. All right, what is the meaning of the slope? So remember, that's the growth rate. Okay, you want to do delta y over delta x. Okay, so we want to say running speed per, because you always do y over x, and per just means the division symbol. So running speed per inch of, you could even just do inch, but inch of animal length. Let's see. They even tell us here, scatter plot is running speed versus, they just use the word length. I'm not sure if they maybe they could have given us a little bit. Oh, here, okay, the graph above shows the relationship between the length of an animal and its running speed. Okay, that would be helpful to know, right? So, but in general, you do y over x. Anytime you want to know what slope is, just put it into words. Running speed versus or per length. All right, what length shows a significantly larger running speed than would be expected from the trend line? I'm not sure it's too significant, but basically they're kind of saying which point is the furthest away from your trend line. That's what that's asking for. So I would say this point here, I don't know, what do we think it is? 23, 24, 25, anything like that, depending on how good my line is. So we could maybe say approximately the 23 inches one. If we had the data, we could actually look and to see what that one is. But do we see why we're talking about this distance here? That distance there, that point was the furthest away from my line of best fit. It's still pretty good, but technically that would be the furthest one away. Probably this one would be the second, right? These two are all pretty close, even though some's maybe a little bit above and a little bit below. These two are probably the furthest away. All right, so now this says, what speed does the trend line predict for an animal that has a length of 58 inches? Okay, so we're going to go back to our trend line. Y equals 2.0298 times, and then our length is 58 inches. I'm just copying it literally from here. And then it's going to be plus, what is it going to be? 5.0873. Okay, and so that turns out to be 122.8 feet per second. Okay. So now what I did here is I tried to calculate, okay, it's great that it's 122 feet per second, but most of the time our brain can comprehend miles per hour. So we're gonna convert this. So I'm gonna start, let's see, can I see it? Yeah, okay. We're going to convert 122.8 feet per second. Okay, we're going to multiply, let's convert feet to miles. So there's 5,280 feet, and I put it on the bottom so that they cancel, in 1 mile. Okay. And now we're going to go all the way back and we're going to convert seconds to hours. So this time, if seconds is on the bottom and I want to get rid of it, it actually has to go on the top. Seconds to minutes. 60 seconds equals 1 minute. Let's cross these out. Let's actually cross, it's okay to cross this out way over here with this one. And now we want to get rid of minutes and we want to go to hours. So minutes is on the bottom, so I actually have to put it on the top. It always has to be opposite. Minutes to hours. Okay. 60 minutes in 1 hour. All right, so minutes cancel. So what's my units not crossed out? The only units not crossed out are miles on the top and hours on the bottom. So that's miles per hour. Miles per hour. All right, and then if I take 122.8 times 60 times 60, let's see if I can squeeze this in here. 122.8 times 60 times 60, and then I had to divide that by everything on the bottom. Everything on the bottom is ones except for the 5,280. So if I divide that out, I get 83.7 miles per hour. Okay. The only thing they're trying to say here, and this is a long way to go at it, but they're trying to say here that at some point, this is pretty fast. This is probably way too fast. So, and this is just data in general, not even necessarily a line of best fit, but at some point, this line might not continue on. This, instead of a line, it might actually be a line segment. At some point, this line continues on, doesn't hold true for all data. So they just kind of want you to be aware of that, that sometimes you really have to think about your restrictions and what's going on. And you might just have to state that this linear only fits an animal between 0 and 50 inches. And then after that, it's no good. So just keep that in mind. That's what they were trying to prove here, that this is a line of best fit for my data. Sometimes we use it to predict, and sometimes we can't. That's all they're getting at there. Okay, let's, and this is kind of what I was talking about before. I like that graph. What do we think? Here's the data. Is this a good line of best fit? Is the above trend line or line of best fit appropriate for that data? And I think we can say no, it's just not good enough. Okay, and so what they want you to realize there, not every set of data is in fact a linear function. Okay, that's just not always possible. So keep that in mind. I think on the homework there's one or two, and then you have to decide, could this be a linear function? Could it be a set of data that fits a linear function? Okay. Okay. Let's see. Okay, so here's the last one. Okay. So here we go. Let's turn this. Okay. As the number of farms has decreased in the United States, the average size of the remaining farms has grown larger, as shown in the table below. So this is time since 1900, okay, and this is the average acre per farm. So the number of farms have decreased, but the remaining has grown larger. All right, the trend line estimates the average size of a farm was 200 acres in 1925 and 365 acres in 1960. So we could actually read that. 1960 is this dot right here, and which is about 365, and 1925 would probably, I don't know, maybe, that's closer to 1930, but 1925 should be 365. Okay. So so the trend line, well, let's mark it. So 1925 oh, hang on. I read that wrong. I'm like, wait a minute, this doesn't add up. Okay. 200 acres in 1925. Okay, that looks a lot better. So here's 1925, here's 200. Actually, I'm glad we did this. Notice I'm talking about the trend line. There is no dot there, and that's okay. I'm talking about the trend line. Okay, in 1960, the trend line, because if you go to this point, I'm like, oh, that's pretty close to 400. But what is the trend line saying? The trend line is saying closer to 365. Okay, but so even though this represents a line, when I go to find the slope, I don't use the points. I have to use the points that are on the line. I do not use the data points. I have to use the points that are on the line. Okay. All right. So here, what they want us to do then is to find slope. Use this information to find the slope of the trend line. So change in y over change in x. Okay. And so let's do this too. Let's write this 200. Let's write it as a point. Now I'm not going to write it as 1925 because this is time since 1900. And notice this also gives us a little bit of clue too. For 1925, I just went to 25 because 1925 is 25 years since 1900. So I'm just going to use, oh, this is on the wrong side, hang on. I'm going to use, because this is x, right, and this is y. So we're going to use 25, comma, 200. Okay. All right, let's try this for the next one. Now let's make sure we get x first, right? X was 1960. So I'm actually only going to use 60 because that's time since 1900. and then my acreage was 365. Okay. And so notice that the data points help me do the line of best fit, but when I actually calculate the slope, I need to use points off of that data line. I have to use points off of the data line. All right, so then we do 365 minus 200, y2 minus y1 over x2 minus x1. So 60 over 25. And then that gives me 165 over 35. We usually like fractions, but in this case, this stuff we just usually do decimals, so 4.71. Okay. All right, the trend line estimates the size of a farm in 1900 to be 88. So again, I'm reading my trend line, which is 88. Find the formula for the acreage of as a linear function of time in years since 1900. Okay, so we're going to do y equals mx plus b. Okay, and then the only thing it has us do is has us change time to t. All right, and time was x. So you could leave this y if they say something else, that would be okay. T plus b. Okay, and then I simply plug in my slope. T. And then, okay, now what is b? B is the y value, because I'm here, the y value at the start of the problem. The y value at the start of the problem, but I have to read it off the line, not my actual data point. I have to read it off the line. So, oh, and they even tell us here. 1900, the trend line says it was right around 88. So 88. There it is. All right, let's slide it up just a little bit. Last one. Use a trend line equation that you wrote in part B to estimate the acreage of the farm in 2010. Okay, so we're just going to use this line, or we're going to use this equation, 4.71t plus 88. Now, the only thing we have to figure out is how many years is it since 1900 to 2010. So if you really need to figure that out, you can do 2010 minus 1900. Okay, and that should give you, most of you can probably just look, but if not, that's okay. That should give us 110, right? Because that would be 100 and then an extra 10. So we just plug that in. Now remember, this is according to the trend line. So this is kind of like a prediction using the trend line. And then just type that in, make sure you multiply and then add, and that should give us 606.18 acres. Okay. Good. All right, see how you do? It's up on WebAssign. If you have questions, just email me. Take care. Bye.